Hey team, welcome to Electro-Knowledge. Today, we're cracking open one of the biggest mysteries for all of us makers. How do capacitors really work with AC?
Okay, so let's just dive right into this with a classic puzzle. And look, this is something that trips up so many of us when we're first starting out. Check this out. On the left, you've got a capacitor and a bulb hooked up to a DC source. The bulb flashes for just a second and then it goes out, right? That makes sense. The capacitor charges up and then boom, it acts like an open switch, blocking any more current. But then you look at the right, same circuit but with an AC source, and that bulb is glowing bright. There's current flowing back and forth, but how? And that is our big mystery for today. I mean, if there's no physical connection, no wire between those two plates, how in the world is current making a complete circuit? Well, here's the secret. It's not actually the same electrons jumping across that gap. Instead, the AC source is constantly pushing and pulling electrons onto and off of the capacitor's plates. This constant charging and discharging on one side of the gap, it causes a matching charge and discharge on the other side. You see, that movement of charge is the current. So now that we know that, let's find the clues to figure out what controls this flow. So the first piece of this puzzle, it's not plain old resistance like you'd see with a resistor. No, it's something way cooler, something that's unique to AC circuits. It's called reactance. The best way to think about capacitive reactance is to imagine it's a smart gate. You know, instead of just a simple wall that blocks everything or lets everything through, this gate is actually frequency sensitive. It decides how much to open up based on how fast that AC signal is changing. And what's really fascinating here is just watching these numbers change. So at a pretty low frequency, say 60 hertz, like what you get from your wall socket, the capacitor puts up a bit of a fight, about 26 ohms of opposition. But look what happens when we crank that frequency all the way up to 2500 hertz. The reactance just plummets to less than 1 ohm. It's basically rolling out the red carpet for that high frequency signal. So the most crucial point to take away from this is higher frequency equals lower reactance. Capacitors basically become superhighways for high-frequency signals, but they act like giant roadblocks for low-frequency ones. And what about DC? Well, DC has a frequency of 0, right? So the reactance is infinite, a total dead end. And that, my friends, is our first major clue. Okay, so now we know what controls the amount of current flowing. But believe it or not, there's another, even weirder piece to this puzzle, and it's all about timing. See, in a simple resistor circuit, voltage and current are partners. They are marching perfectly in step. But with a capacitor, oh no, they are totally out of sync. And this right here perfectly illustrates our second clue. The current gets a head start. And if you think about it, it has to, right? For a voltage to even build up across the capacitor, charge has to be moved onto its plates first. And what is that movement of charge? It's current. So the current has to happen first to cause the voltage. It actually reaches its peak a full quarter cycle before the voltage does. This 90-degree lead, it's the fundamental secret to a capacitor's power in AC circuits. But let's be real for a second. Trying to remember if current leads voltage or voltage leads current, especially when we start throwing inductors into the mix, well, that's just a recipe for a headache. We need a way to lock this into our memory for good. All right, it's time for the grand reveal. Get ready for the one trick that every single electronics pro uses to keep this stuff straight. Seriously, this is a total game changer. This is it. This is the key that unlocks everything. It's a simple little phrase that is going to save you so many headaches down the line. Just say it with me. Eli the Iceman. This little phrase is pure gold, and for our capacitor mystery today, we are zeroing in on that second half. Ice, that's I-C-E, current, which is I, in a capacitor, C, comes before voltage, E. It is really that simple. Current leads voltage. You will never, ever forget it now. And that Eli part, well, that's for inductors, but that's a deep dive for another time. And that's the core concept. Ice gives us the what. So now let's get to the so what. Why does any of this actually matter when we're sitting at our workbench trying to build something? Now we get to the payoff. We've solved the mystery. So let's see how we can use this newfound knowledge to build some seriously cool stuff. So because capacitors treat different frequencies, well, differently, we can actually weaponize this behavior to build filters. Let's say you want to get rid of some high-frequency noise. Easy. You can use a capacitor as a low-pass filter, which gives that noise a super easy path to ground. Or maybe you want to block DC and let only your audio signal through? Just use a capacitor as a high-pass filter. It's kind of like having a bouncer for frequencies at the door of your circuit.
And this, right here, is why all of this matters so much for our projects. We use these exact principles for everything, from smoothing out the power for our microcontrollers to building the audio crossovers that make our speakers absolutely sing. This isn't just theory, folks. This is the very foundation of modern electronics.
All right, let's do a super quick recap of our mission today.
We started with a mystery. How is current flowing through a gap? Then we found clues in reactance and phase shift. We unlocked the whole thing with ice. And then we saw how it all pays off in our real-world projects. We went from a confusing puzzle to an incredibly powerful design tool. So this knowledge is basically a new superpower in your toolkit. The only question now is, how are you going to use it? I mean, think about that audio crossover you've always wanted to build, or that noisy power supply that you've been meaning to fix. What's the first project that you're inspired to build or improve?